good morning. Today we are going to study stereoisomerism. Structural isomerism completed. Next one is stereoisomerism. In the stereoisomerism, it is given that organic compounds having the same molecular formula, but the arrangement of atom in space will be different. So such compounds are called stereoisomers, and the phenomenon is called stereoisomer. So the organic compounds having same molecular formula but differ in the arrangement of atoms in space are called stereoisomers. And there are two types of the stereoisomers. There are two types. One is the geometrical isomerism. Geometrical isomerism. And second one is the optical isomerism. So first of all, we will take geometrical isomerism. So in the geometrical isomerism, the compound must contain carbon-carbon double bond. The compound must contain carbon-carbon double bond. So geometrical isomerism. So this geometrical isomerism, that compound must have carbon-carbon double bond. Then this geometrical isomerism, due to restricted rotation about carbon-carbon double bond. It means the rotation between the two carbon atom is not free, and compound of the type AB C double bond C AB or AX C double bond A1, they will show the geometrical isomerism. So just to see what is the restricted rotation. So if you take the two carbon atoms, between the two carbon atom double bond is there. So if you want to rotate, you cannot rotate it. But if the single carbon is there, and between the carbon atom, if the single bond is there, it can be rotated, free rotation is there. But if the double bond is there, so this double bond, restricted rotation will be there, free rotation will not be there. So what happened here, the compounds, forming organic compounds, they must have the carbon-carbon double bond, and this is due to the restricted rotation about the carbon-carbon bond, and the compound of the type, this will show the geometrical isomerism. So first of all, what is the definition of the geometrical isomerism? So the organic compounds having same molecular formula, but differ in arrangement of atoms, differ in arrangement of atoms atoms around the carbon-carbon double bond. Around the carbon-carbon double bond. The organic compounds having same molecular formula but differ in arrangement of atoms or group of atoms around the carbon-carbon double bond are called geometrical isomers. Are called geometrical isomers. And the phenomenon is called geometrical isomerism. This geometrical isomerism is also called cis-trans isomerism. Geometrical isomerism is also called cis-trans isomerism. So what is cis and trans? When the similar groups are put in the same side of the carbon atom, it is called cis. And when the similar groups are put in the opposite side of the carbon atom, it is called the when similar groups atoms when similar groups are present on the same side of carbon-carbon double bond called cis isomer. When the similar groups are present on the opposite sides, of the carbon-carbon double bond, when similar groups are present on the opposite side of carbon-carbon double bond called trans isomer. So just to see, in the carbon-carbon double bond, when the similar groups are present on the same side, it is called cis. And the similar groups are present on the opposite side, it is called trans. So first of all, this one example, this carbon-carbon double bond is there and the similar groups are present on the same side. This A and B. This one is called cis. Then next one is these similar groups are present on the opposite side. So this similar groups, the opposite side, this one is trans. One more example we have taken AX C double bond C, AX and AY. So here just you see this carbon-carbon double bond, similar groups are present on the same side of the carbon-carbon double bond. So this one is called cis. And if the similar groups are present on the opposite side, this one is called trans. So by this it is very simple. This carbon-carbon double bond, similar groups are on the same side, cis. Similar groups are on the opposite side, trans. So some example of the geometrical isomerism. First of all, but2in. Examples are geometrical isomerism. Examples are geometrical isomerism. Examples are geometrical isomerism. So, first of all, very simple. Butte 2E. First we draw structure of the butte 2E. So this one is CS3CH, CH, CS3. So this butte 2E is here. From this carbon atom, two groups are bonded, CS3 and H. From this carbon atom, CS3 and H. So let us make the cis and trans. This carbon double bond H, CS3, ELH, CS3. So similar atoms on the same side of the carbon double bond. This one is cis butte 2E. Then another one is that carbon double bond H, CS3, CS3. This one is called trans butte 2E. Now next one is 1,2 dibromoethane. Draw the geometrical isomers of 1,2 dibromoethane. So next one is 1,2 dibromoethane. 1,2 dibromoethane. So just to see the structure of 1,2 dibromoethane, this one is bromine 1,2. So this is the compound 1,2 dibromoethane. So we can draw the cis and trans. H, Br. This one is cis 1,2 dibromoethane. Then carbon double bond BrH, BrH. This one is trans 1,2 dibromoethane. Dibromoethane. Now next example is that butte 2E oic acid. Butte 2E oic acid. So butte 2E oic acid. Nothing is given. It means that carboxylic will present on the first carbon. So the structure of this one is 4 carbon, 1, 2, 3, 4. Butte 2E, second carbon double bond, first carboxylic group. Now you can put the hydrogen atoms here. 1, CS. So butte 2E, not oic. Butte 2E 1,4 dioic acid. So this example, this butte 2E 1,4 dioic acid. So this is very important. Just to see carbon double bond, then H, C double OH, then H, C double OH. So this one is the cis. This compound will be there. And when it is in a cis form, it is called maleic acid. C double OH, H, here C double OH. So this one is trans but 2-in-1,4-diol acid. This is called fumaric acid. So this is important. They may ask you, get the structure of the maleic acid and fumaric acid. So maleic and fumaric acid, they are coming from the same compound. The difference is that when you take the cis isomer, it is called maleic acid, and when you take the trans isomer, it is called fumaric acid. So three examples I have shown here. Now third one you can do, fourth one you can do by yourself from your book. But-2-enoic acid, so that you can do. Next one is conditions for geometrical isomerism. Conditions for geometrical isomerism. Conditions for geometrical isomerism. Conditions for geometrical isomerism. So the first one, that compounds must have carbon-carbon double bond. This is necessary condition. Then only geometrical isomerism is possible. And then compounds of the type AB, C, AB or AX, C, A. So compounds must have the carbon-carbon double bond, and the compounds of the type that carbon-carbon double bond and the atoms are the two bonded to the carbon-carbon double bond must be different. Then only the geometrical isomerism will be possible. And suppose that if here similar groups are there, either here or there, then geometrical isomerism will not be possible. So this compound AA, AB or AB, C, C, EB. This compound will not show the geometrical isomerism. This compound will not show the geometrical isomerism. Here, such type of compounds will not show geometrical isomerism. Geometrical isomerism. So this is the condition that the compound must have the carbon-carbon double bond. If the carbon-carbon double bond is there, then only restricted rotation is there, and then the group or the atoms bonded to the carbon-carbon double bond, they must be different. AB, then only geometrical isomerism is possible. So such type of the example I am going to take but-1-in and propene. So first example, propene. Propene structure is CH3, CH, CH2. So just to draw the cis and trans isomer of this propene. So this carbon-carbon double bond, two hydrogen atoms, here H and here CH3. If you are thinking cis, so just you see, I will take this one here. So this I will take here CH3 and H here. Again it becomes cis. So here cis trans is not possible if the atoms or the group of atoms bonded to the carbon-carbon double bond both are same. Because in both the cases you cannot differentiate which one is cis and which one is trans. So in such compound, geometrical isomerism is not possible. So for geometrical isomerism, it is necessary that the group of atoms or the atoms which are bonded to the carbon-carbon double bond must be different. Now one more example that you can take but1ene. This is the first example. Now the second example, that but1ene. So what is the structure of but1ene? This CH3, CH2, CH double bond CH2. This compound is but1ene. Now just to see whether the cis trans isomerism is possible. So this carbon-carbon double bond, from that carbon atom two hydrogen atoms. From this one is one C2H5 and one H is there. Now again you can take carbon-carbon double bond. Here I am taking C2H5, that one, that side. So C2H5H. Now you are thinking that similar groups are to the same side of carbon atom cis, then here also cis. So that's why such compounds, such type of compounds will not show a geometrical isomerism. The condition is that the atoms or the group of atoms bonded to the carbon-carbon double bond must be different, then only geometrical isomerism is possible. So now next one is cause of geometrical isomerism. So here this last two geometrical isomerism is possible. So next one is cause of geometrical isomerism. Cause of geometrical isomerism. Cause of geometrical isomerism. Cause of geometrical isomerism. So this geometrical isomerism is there due to restricted rotation of the carbon-carbon double bond. This is due to restricted rotation about. This is due to restricted rotation about carbon-carbon double bond. Then why this restricted rotation is there? This restricted rotation is there because of the formation of pi bond. And to break the pi bond, 251 kilojoule energy is required. The restricted rotation is due to pi bond. To break the pi bond, the energy required is 251 kilojoule per mole. This much amount of energy is not obtained at normal condition by the molecules. These molecules are having a thermal motion, so they are not having this much amount of energy to break the pi bond. So how it is possible? You know that in alkene, this carbon-carbon double bond is there. So this carbon atom is sp2 hybridized. One rule is there that 4 sigma bond sp3, 3 sigma bond sp2, 2 sigma bond sp. So this carbon atom is sp2 hybridized. So ground state 1s2, 2s2, 2p2. So this is the ground state. 2 electrons here, 2 here. Now you can take the excited state. Ground state. Now you can take excited state. So just to see the excited state, one electron will be promoted from 2s to 2p. So this is 1s2, 2s1, 2p3. Now 4 electrons are there. Since you studied that this is sp2 hybridized, then 1s and 2p orbital will be mixed, and this carbon in hybrid state. So what will happen? This 1s2 and these 3 orbitals will be mixed, and one either take 2py or 2ps perpendicular to the plane. So this one is sp2 hybrid orbital. So what is the shape of sp2 hybrid orbital? Already you studied that sp2 hybrid orbital, that in trigonal planar shape is there. So these carbon atoms, this sp2, look, sp2, sp2. Then this carbon atom, sp2, and this. Now here some groups will come. Then one unhybridized p orbital is there. So what will happen? This carbon, here some groups will come, and this is called the restricted rotation. This is called the restricted rotation. This A, B, B. So this carbon and A and B atoms, they are present in the same plane of the plane. But this 2py orbital, these are perpendicular to the plane of this paper or plane of this board. So they are not free to move. This is the pi bond. To break this pi bond, 251 kilojoule energy is required, and this much energy cannot be obtained by the thermal motion of the molecule or by any other method. So that's why this restricted rotation. Hindered rotation is possible. So because of this hindered rotation, they are giving cis-trans isomerism. So the main cause for this geometrical isomerism, hindered rotation, and this hindered rotation is there because of the pi bond. This hindered rotation is there because of the pi bond. This pi bond is there. Hindered rotation is there. And to break this pi bond, energy required 251 kilojoule per mole. And this much energy is not obtained at the normal condition. So that's why this alkenes will show the geometrical isomerism. So you can see your book what I have given today. It is given page number 728 and page number 729. Now next one is the properties are given, so that we will take it next week.